Hi everyone. Welcome to a lecture that describes a materials degradation mechanism that limits the longevity of a number of applications. It was first observed at the dawn of the railways, but even today it can still present dramatic failures. Here is a failed railway axle, which was documented in 2017 in Australia. The reason why this axle failed was because of an unobserved fatigue crack, which propagated and then led to the relatively dramatic failure depicted here. You might think this is a new problem, but it's quite a historic phenomenon. Fatigue is a process by which a material fails progressively under repeated loading, often well below the yield strength, and therefore can go undetected well until it's too late. Joseph Glynn first illustrated this type of failure over 170 years ago in an early railway component. In this lecture, we'll cover why this type of failure occurs at all, and why it's particularly important to appreciate, not just in the transportation sector, but anywhere a component has been designed to withstand repeated loads. This is a very encompassing description. At the beginning of the railway age, the British were still trying to keep their steam engines from exploding, but the French had another type of failure: fatigue in engine axles, as illustrated by Joseph Glynn earlier. After dozens of passengers perished in the Versailles crash in 1842, there were numerous conflicting opinions as to the root cause. August Wohler, a German engineer, was the first to come up with an empirical technique to assess this phenomenon. He devised a methodology to check the number of cycles to failure for a given component loaded under the same conditions as the railway component. The system operated on the basis of a loaded component as depicted, which should then be spun at a high rate and the number of cycles to failure tabulated. The specimen would have half of its gauge in compression and the other half in tension at any given point in time. Over the intervening 150 years or so since being popularized as an assessment technique, much of the data that we have on fatigue has been generated with this type of testing. But it is important to highlight that this is in fact a conservative test for anything but the component for which Wohler first devised the test for. In this lecture, we'll see why. Any cyclic load will appear in this manner, ranging from tension to compression, or depending on what the mean stress is, being more in tension than compression at any given point in time. Thinking about our Australian railway axle, at any point in it, it changes between tension and compression on a cyclic basis. The amplitude is defined by the difference between the maximum and minimum stress. The mean stress is defined as the average stress achieved. The fatigue regime, that is, the loading conditions that are operating, can be categorized by the load ratio, R, which is the ratio of the minimum stress versus the maximum. While fully reversed loading, that is, the magnitude of maximum tensile stress is equal to the compressive stress, is indicative of a Wohler-type scenario. It is the least aggressive fatigue condition. In fact, the more tensile a fatigue cycle is, then there will be fewer cycles that can be withstood before failure. Let's now examine how a load can change across a cross-section of a small portion of material. If the material is monolithic, that is, has a constant cross-section, then we can draw isolines of constant force across it. If there's a small flaw on the side of the material as depicted, then the isolines will have to bend and concentrate immediately approximate to the flaw. This means that the stress will appear locally much higher near this flaw. Let's now look at how this type of flaw can appear and how it relates to fatigue. If you recall the lecture on plasticity, I described that slip occurs on favorably oriented slip planes. In a polycrystalline material, some grains have their orientation such that slip is achievable once the yield stress is achieved. However, as we know, there are many grains that make up a metal, and there can be a grain or several grains that have their orientations such that slip can occur below the overall yield stress of the material. Cyclic loading will cause this slip to localize and start to create a flaw-like feature on the surface. With a stress concentration, this means that the local stress around the flaw can increase beyond the yield stress. This is Woods' theory, which explains why fatigue cracks initiate and explains why fatigue cracks appear near the surface of materials. We'll cover other microstructural features that can also create these types of stress concentrations in a future lecture. But for now, let's examine how these cracks can propagate. Cracks will initiate, grow, and then once a critical size is achieved, it will cause the crack to envelop the entire cross-section of a component. From the features on these two fracture surfaces, it can be seen that there are features that show where the cracks initiate and then propagate at different rates. The type of loading will dictate the morphology features, but it's clear that the crack will propagate at different rates. Plotting the rate at which a crack will grow relative to the number of cycles for a given loading scenario, there are two main types of behavior depending on the material. Some materials have cracks which grow slowly and steadily until the final point of failure. Others are initiation dominated, which means that the overall fatigue lifetime is dominated by growing a crack to a critical point and then it accelerates. The top right fracture surface shows this type of behavior. The crack is grown slowly at first and then only required a few cycles to completely encompass the surface. Materials that exhibit this type of initiation, followed by fast fracture, are typically those which are high strength and therefore have lower ductility, or materials that have BCC and HCP crystal structures. FCC-type materials typically have propagation-dominated behavior. Here, the fracture surface of an aluminium alloy near an initiating defect is shown. The striations appearing on the fracture surface show that the crack has grown regularly and can be tabulated to assess growth rates if the number of cycles are known. This isn't the most prevalent way of assessing fatigue behavior, as it will only assess a limited amount of material. The way that fatigue behavior for design purposes is tabulated is by relating some stress characteristic of a fatigue test versus the cycles to failure. While I've shown stress amplitude on the vertical axis, this could also be maximum stress or some other facet of the test regime. There are two different types of fatigue curves. One that is associated with a ferrous material which has a fatigue limit, and for non-ferrous materials, one that does not demonstrate this fatigue limit. Instead, fatigue lives are characterized by an endurance limit. That is, for a characteristic stress, there will be a number of cycles to failure. The endurance limit for N1 cycles, for example, is S1, and S2 for N2. For ferrous materials, if the stress is kept below the fatigue limit, then it will be able to withstand an effectively infinite number of cycles. Each of these SN curves aren't derived by a single set of tests, but are captured by numerous specimens. As we've seen from Woods' theory, there are some material conditions which are stochastic, that is, ruled by chance and probability. For any material system, there is a chance that the microstructure will fail at a higher or lower stress for a given number of cycles and vice versa. So, the SN curve is viewed as a representation of a probability density function, either for the stress or numbers of cycles that can be withstood before failure. As I mentioned earlier, there are some conditions that are more aggressive and can lead to fatigue occurring earlier. Here are two non-ferrous SN curves. The top is for a fully reversed condition, as indicated by the load ratio R. This means that the curve was found from testing where each cycle had a mean stress of 0, or the tensile stress was equal to the compressive. Below this is the result from a different load ratio of 0.1. This scenario has the material experiencing a non-zero mean stress, or the material is under more tension than compression at any given point in time. For the same number of cycles, a material will withstand a higher stress amplitude at R equals -1 versus R equals 0.1. This is because of the mean stress effect. If the mean stress is 0, then the material spends half of every cycle in a condition where the crack does not open. Cracks only propagate in tension, as shown on the top, or some of the more complicated modes, as I've shown below this. We'll get into this further when we discuss fracture. This is why the results from a Wohler test are conservative. Only half of the material is in tension at any given point in time, meaning that an SN curve derived from Wohler results will predict higher stresses to failure for a given number of cycles as compared to an equivalent uniaxial stress state. So, we have studied a degradation mechanism that involves the gradual accumulation of damage to a material due to cyclic loading, occurring well below the yield strength of material. We have seen how different types of material react to this type of damage through different propagation rates of fatigue cracks. Some are initiation dominated and others are propagation dominated. We have reviewed how fatigue behavior is characterized by SN curves, and that the most aggressive conditions for any material is when the load ratio, or the ratio between the minimum and maximum stress, is greater than -1. This is because compression does not serve to open cracks, only tensile stresses do. We'll discuss fracture further in an upcoming lecture. Until next time.